think he was. But anyways, yo, Thumbelina looked like a pretty cool movie. I ain't never seen that before. That is messed up how like these little kid movies kind of treat real life in essence. Like Shorty was really being trafficked by all these people. It's like the Hollywood industry. Now we're gonna force you to go out there and sing. Now we're gonna force you to put this outfit on for this big show. We're gonna force you to do that.
Look at the old buildings from 1893, 1895, 1896, that whole time. So you build a building that has maybe 1,000 rooms or something crazy. And there's no sanitation or sewage, there's no toilets in that. Then you put the toilets in bathrooms. You're very advanced society that's building these buildings. You have dirt roads, all this other stuff, but you have no toilets. Almost like you're out of this world that don't belong. That's the only reason when you start to think about that, why you would have no sanitation. Look at the old buildings from 1893, 1895, 1896, that whole time. They don't have toilets. So you build a building that has maybe 1,000 rooms or something crazy. And there's no sanitation or sewage system. There's no toilets in that. Then you put the toilets in bathrooms. You're a very advanced society that's building these buildings. You have dirt roads, all this other stuff, but you have no toilets.
All right, gentlemen, I'll be right with you. Just give me just a few more moments. So. Join. Audio. See as a participant. All right. Testing. Mic check. 1, 2. Okay, that's not what I said, but that's close enough. Okay. All right, gentlemen, let's see. So welcome. So I went on and calculated midterm grades. I just did it based on anything that was due. So mainly the first 3 sections, so section 1-1, 1-2, and 1-3, and exam 1. And I kind of adjusted the weights. The weights are like, I think I made the homework average, that was like 10% of the overall grade. The quiz average was 10% of the overall grade. And then the exam average, I think I made it 80%, right? Something like that. So it's, it's not 100% accurate. It's just close to the true score. We really won't be able to get the true score until we get everything submitted, like including the final exam. So this is really just a gauge of where we are at this moment in time. It has no bearing on the grade that really matters, which is the final grade. So I say that to say, it's a good idea to go onto Blackboard and check your grades for accuracy. The main thing that you need on your end is that the grades that you've earned in my math lab have shown up in Blackboard, right? And again, really right now it's just a snapshot of where you are in time. It's going to be a little bit skewed just because we don't have all the assignments submitted. We won't be able to get it 100% accurate until we submit the final exam. All right, so again, this is just a gauge of where you are. So then on your end, if you see that you're like missing something, or if anything just looks kind of like out of source or out of place, then you just bring it to my attention and we can like make sure to straighten it all out. Also, it should be like a live update. So, like, as you go and change and submit past assignments or anything of that nature, it it should be a live update of your grade. All right. So maybe I can go ahead and load the future assignments. I don't know. We'll cross those bridges when we get to them. So I am using my microphone. I am using my microphone today. So if you have questions, just feel free to either put it in the chat or put it in Q&A. And there'll be an opportunity to kind of chat at the end of class and see if there's anything else. The main thing is, I just updated midterm grades, and so like, if your grade is lower than what you would like, then keep in mind that with all of our assignments, we get unlimited attempts. The system is set to take your highest score. You can, if you got less than a 95% on any assignment, you can go back and do it as many times as you like until you get whatever score you like. Right, so that's something to definitely take advantage of. Okay. So I can't think of anything else. I think I hit like the main points. And so this week, so we're going to basically be continuing with the next installment. I know. Hope everyone is doing well. Also, like with this like chemical fire that happened out in Lithonia, I drove past it. Like I was out there. I saw that because at first I got the alert. I was kind of like going around. Then I saw this alert about a fire. I was like, okay, I looked over the horizon, from wherever I was at, and I was like, oh, there is a huge plume of smoke. So we kind of like made our way away from it for most of the day. So I was just like, it's unnerving, and they always made these things try to seem like it's accidental, but anybody with any sense of intuitiveness knows more than likely was not accidental, right? So, but you just kind of take it case by case and don't worry about it and just do the best you can and just keep it moving. That's all you can really do. Okay. So I think last time we talked about section 1.4, library of functions. So that's where we had the list of, base functions. Sometimes I refer to them as base functions or parent functions. And we had the constant function, identity function, squaring function, cubing function, square root function, absolute value function, cube root function. And we also talked about the step function, greatest integer function, which is like, the step function. Right. And I think that's it. So, and the reciprocal function, right? So these are just a list of functions that we talked about last time because we're basically developing or building a case for graphing functions, right? And the very first technique that we have for graphing a function was plotting points. So choosing several values of x, find the corresponding y. If these points are on a line, we connect the dots with a straight edge. If they're on a curve, then we just connect the dots with a smooth curve, right? So this next installment, we're going to take those base functions and start to manipulate them, okay? So here we have section 1.5, transformations of functions. A few objectives. 1, define transformations of graphs. 2, use vertical or horizontal shifts to graph functions. 3, use reflections to graph functions. And 4, use stretching or compressing to graph functions, okay? So then transformations, if a new function is formed by performing certain operations on a given function f, then the graph of the new function is called the transformation of the graph of f. So given this base function, absolute value of x, we also want to consider g of x, which is the absolute value of x plus 2, and h of x, which is the absolute value of x minus 3. And here we're asked to sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Right, so the parent function here that's given, right, is absolute value. Can anybody describe the shape of absolute value in the chat real quick, like in your own words? Like, what's the general shape of that? What does that look like from last time? All right, absolute value. And it's like you can even just you can just type a letter that would suffice, right? It looks like a V, right? Yeah, okay, I see you. All right, so it looks like a V. Now the way I'm getting a little bit distracted because this is making me think of The Circle. I think they have the finale of season 7 that comes out on like October 2nd. So I finally got caught up over the weekend. I want to talk about that too. We'll talk about that later. But yeah, so absolute value looks like a V, right? So The base function is just a v with the vertex at the origin. And then we're going to see, okay, if we add, no, now with these two functions, right, with that first one, we're adding a positive number on the outside of our base function, right? So the base function is absolute value. We added 2 on the outside. We're going to see how that affects the graph. And then we also want to see if we subtract a positive on the outside of our base function. So notice, I really want you to kind of hone in on me stressing that these are outside manipulations, and we're going to see how it affects the graph, okay? So a way that we can go about this, we can choose several values of x, and then pass each x through each function to generate the corresponding y, plot the points, and connect the dots in a proper manner. Okay, so we're going to make a table of values and graph the equation. So we let x be -5, -3, -1, 0, 1, 3, 5. So absolute value, right? Absolute value is the positive distance away from 0 a number is. So for instance, the absolute value of -5 is 5 units away from 0. So that's why that was 5. Absolute value of -3 is 3, so on and so on and so on. So then to generate g, we're basically going to take those results that we got from the middle column and add 2 to it. So notice that in this case, our x values are staying the same, but the y values are increasing by 2. So in the chat, can somebody describe to me, when we added a positive number on the outside of our base function, how did it affect the blue graph? How could you describe how we went from the blue graph to the red graph? Right? What effect did it take? Right. So again, the x value stayed the same, but every y value was increased by 2, right? So it moved up along the y-axis, right? That's fine, right? So we adding a positive number on the outside of our base function, it basically shifted the graph up by 2 units, right? So when it comes to transformations, there are a total of 10 transformations altogether. Each transformation in and of itself is simple. The challenge comes because many students experience information overload. Like if you just had just one transformation that you were focused on and we talked about it, fairly simple to process, right? But again, with there being 10 of them, students tend to shut down. And so the only way I personally know to kind of combat that information overload is just to give yourself as much time. You got to kind of just start processing this stuff as early as possible, because if we procrastinate, then you don't want your first time making a mistake on this to be at a critical moment, like an exam or a proctored exam or a job interview, right? Whenever we're going to be responsible for this, the first time we try this stuff, we're going to make mistakes, right? So the goal is to get past those mistakes as early as possible, so that way when you need this information, you'll have it ready at your disposal. But if you procrastinate, if you avoid it, when you need this information, and that's more than likely going to be your first time making a mistake, and you're not going to be able to perform when you need it, right? So so this kind of illustrates our first transformation. Again, adding a positive number on the outside of our base function, it caused a vertical change by that many units, right? So it moved the entire graph up that many units, okay? So adding a positive on the outside caused a vertical change. Then intuitively, what do you think happens when we subtract a positive on the outside? If adding a positive moved it up that many units, then what do you think happens when we subtract a positive on the outside? It should go what many units? Which direction should it go? All right. Okay. So I feel like it sunk in. So hopefully everybody has a notion there. All right. Okay. So let's just see what happens. All right. So if we subtract a positive, so adding a positive on the outside causes the entire graph to move up that many units. So subtracting a positive on the outside causes our function to move down that many units, right? So again, outside manipulations cause a vertical change and they follow our intuition. So if outside manipulations cause a vertical change and they follow our intuition, then what do you think happens if we do inside manipulations? let me pose that question one more time. If outside manipulations cause a vertical change and they follow our intuition, then what type of change can you anticipate when we do an inside
Where your
manipulation?
monitor at?
And
Where your monitor?
Okay, so hopefully you got something there. Let's kind of go forward a little bit. All right. So keeping in track of what we just did a moment ago, given a positive number, if we add a positive on the outside of our base function, it's going to shift the original function up that many units. Subtracting a positive on the outside of our base function shifts our original function down that many units. Okay. So now in the previous example, we looked at absolute value, all right? And we looked at outside manipulations causing it to move up and down. Here, our base function is squared, right? F of x equals x squared, right? So like, what's the basic shape? If the last one was a V, how could you describe this basic shape? And then we're also going to see, if we subtract a positive on the inside of our base function, how does it affect the graph? If we add a positive on the inside of our base function, how does it affect the graph, right? Okay. So what do you think is going to happen? Let's start with the subtracting a positive on the inside. If we subtract a positive on the inside, what does your intuition tell you how it's going to affect the original graph? All right. Anybody got a result there? Let's take a few seconds. I'm just curious. So again, let's pose the question again. If we subtract a positive on the inside of our base function, what does your intuition tell you as far as how that's going to affect the graph? What's going to happen? All right. Take a few more seconds. Okay. So it's okay. So let's see if we can get a sense of it. So what we can do here, we have our base function, which is x squared, right? Hopefully you're thinking parabola, U-shaped curve, okay? And we're going to choose several values of x, find the corresponding y, and then the first manipulation is we subtracted 2 on the inside, right? So we chose our values of x, we found the corresponding y, and then
Fred.
so notice with the subtracting 2 is it's changing our x values, right? So we're subtracted 2, so that is -4 minus 2 is going to give us -6 squared, which is a positive 36. All right, so remember in the previous example, our x values stayed the same and only our y values changed. So here, you can essentially say the same thing. Well, our x values are changing and our y values are essentially staying the same, right? It restarts kind of a little bit further down, right? So you can see the 16 shifted down by 2 in the chart, and on the right hand side, it shifted in that manner. So with these, the x values are changing, but the y values are staying the same, right? So then how do you think, if we subtract a positive 2 on the inside, how does it affect the graph? Let's take a look. So the blue is our original, right? Subtracting a 2 on the inside, intuitively you might think, oh, well, maybe it moves in the negative x direction, it moves to the left by 2, where in reality, it moves to the right by 2, all right? So I think before we said outside manipulations cause a vertical change and they follow our intuition. Well, inside manipulations cause a horizontal change and they're the reverse of our intuition, all right, which is not obvious. So, intuitively, at first glance, the green, you might think, oh, well, if we're subtracting 2 on the inside, it should move towards the negative x direction. In reality, it moves 2 units in the positive x direction. One way you can kind of like process this is like, okay, you ask yourself what value of x makes the inside 0. So then positive 2 would make the inside 0. So if you track the vertex, then it's essentially moving to the right by 2. When you start doing these transformations on your own and you get a result, choose a few points on your graph that you can test. You can plug into the original, into the function and make sure that it all kind of lines up, right? So, subtracting a positive on the inside moved it to the right 2 units. Adding a positive on the inside moved it to the left, right? So at this point, we've talked about 4 of the 10 total transformations for our graphs. We'll do a quick recap on the 4. The first one was adding a positive on the outside, move the entire graph up that many units. Subtracting a positive on the outside of our base function, move the original graph down that many units, right? Subtracting a positive on the inside, moved it in the positive direction, and adding a positive on the inside moved it in the negative x direction. All right. So again, inside causes a horizontal change, and it's typically the reverse of our intuition. Right. So that's a recap of the 4 transformations where we did 2 manipulations on the outside, 2 manipulations on the inside. So then, let me see. Yeah, this is okay. That's essentially what we just did. Okay. So given a positive number, the graph of f of x minus c, notice that we're subtracting a positive on the inside. That's going to shift the original function c units to the right. And then adding a positive on the inside, it's going to shift the original function c units to the left. Okay. Can anybody, so in this example, can anybody in the chat describe to me the basic shape of square root function, right? So this is another one of our parent functions or base functions. Can anybody describe to me the shape of the square root function in their own words, all right? Just take a moment. What does the square root function generally look like? Or can you describe how you remember that basic shape? All right. Okay, the chat is going there first. All right. So the way that I like to personally remember the general shape of square root is kind of given in the symbol a little bit. The basic shape of a square root function, the way I remember it, is the top half of a sideways parabola, right? So if you took a U-shaped curve, you turned it to the right, and you cut it in half horizontally, you only keep the top half. That's the general shape of a square root function, right? So the square root function is our base function here, okay? And then we have multiple transformations that we want to account for, all right? I'll give you a hint, there are 2. Can anybody in the chat describe like, okay, what are the transformations? It's 3 things. What are the transformations? How do they affect the graph? And give me the transformations in the proper order. Okay, so just take a moment to think about that. If you feel confident, feel free to submit it. Let me say that one more time. So there are 3 things we're looking for. What are the transformations, that we're doing on the square root function? How does it affect the graph? And then can you give those results, provide them in the proper order? Okay, and I'll give some more hint here. So when we're doing multiple transformations in one function, the recommendation is to start with the innermost nested transformation first and work your way out. Right? So if we start with the innermost nested transformation, right, which result is that? I see people dropping like flies. But that may not be the case, because I know that sometimes people have multiple devices. So again, this information is like, in and of itself, it's simple, but then when you start stringing it together, it's like it gets to be a little bit excessive. So just do the best you can with it. This is definitely something you want to process, though. It keeps popping back up. This is College Algebra 1. We definitely use it in College Algebra 2. So yeah, some multiple transformations at play here. Again, the recommendation is to start with the innermost nested transformation, whichever is the closest to the inside, and then work your way out. So the innermost nested transformation in this case is going to be that +2 on the inside, right? So if we add 2 on the inside, that means it's going to cause a horizontal change. Yeah, let me see. Give me just a moment. Let me reply to this. Because if I don't do it now, I won't forget. Give me just a moment. I'm going to say, look at it after 2 to 3, 3 to 4, after 4 p.m. Okay. Yeah, so you definitely want to check your grades for accuracy. Also, when it comes to the grades, you got to be aware of the weight of it as well. I think for you all, I made the homework worth 10%, the quizzes worth 10%, and then the exams worth like 60%. I know that's not That's not the full 100. Again, it's not the full 100% because we haven't taken the final yet. So, but I say that to say I want you to be aware that the exams have a much heavier weight than the homework. So, like if you've done your homework and quizzes, but you either haven't done the exam or you bombed the exam, you might want to go back and try to boost that score for the exam, and you'll see a huge boost in your overall score. Versus the homework is going to be a lot of work, but you won't see the score change a lot. Right. So that's one of the things that I'm glad he at least messaged, and I can kind of pass on that information to you all as far as the grading, right? So if you are trying to go back and boost your score, top priority are the exams because those have a much heavier weight than anything else, right? Okay, so back to this one. So we're starting with the parent function, the square root function, where it basically starts at the origin. That +2 tells us we're going to move the original graph left 2 units, all right? And then we subtracted the 3 on the outside of our base function, so that's going to move the entire graph down 3 units. So long story short, top half of a sideways parabola starting at the origin, then we just move the entire graph left 2 units and then down 3 units, and then we're done. Okay. And you can see that here. Well, good Tucker. Oh. All right. So the black is where we started. Blue was after the first manipulation, the first transformation with that moving it left 2 units. And then the red, we moved it down 3 units, and that's our final graph. Okay. So, again, when you start doing transformations, say you get a final graph and you're still a little bit hesitant about it, what you could do is like choose a few test points, like choose several values of X, find the corresponding Y, and then if you plot those points, you should be plotting it on your graph, right? It should all line up. And if it doesn't line up, either you did the calculation wrong or you did the graph wrong. You have to go back and get to the bottom of where the error is and kind of correct it. Okay. So again, we've talked about four of the 10 transformations. When we added a positive on the outside, the X value stayed the same, but only the Y values changed. Similar for the next one. But then when we started doing inside manipulations, the X value changed, but the Y values stayed the same, right? So then here, we want to explore, well, what happens when we multiply the outside by a negative, right? So again, as a recap, outside manipulations typically cause a vertical change and they follow our intuition. So if we're multiplying the outside by a negative, it's like our Y values are going from positive Y to negative Y. The X values are staying the same, but the Y's are going from positive to negative, right? Can anybody describe to me that change in the graph in their own words? If we were multiplying the outside by a negative and the Y's are going from positive to negative, how could you describe that, right? Right. So if our X values are staying the same and the Y's are going from positive to negative, then basically what that's doing is taking our entire graph and flipping it vertically over the X-axis, all right? It's flipping it vertically over the X-axis. So here's a pictorial representation of that. F is our original graph. Notice our X values are staying the same, but our Y values are going from positive Y to negative Y. So then it basically flips the entire graph vertically over the X-axis. Okay. So then we've explored multiplying the outside by a negative. So then let's explore what happens when we multiply the inside by a negative. So inside manipulations typically cause a horizontal change, and they're the reverse of our intuition. So this one, multiplying the inside, it does cause the graph to flip horizontally, right? And I think that does kind of go with our intuition, but it still causes a horizontal change. So here's an example, right? So then we have Y equals F of X. If we multiply the inside by a negative, our Y values stay the same, but our X values go from positive to negative. So it flips horizontally over the Y axis. Okay. We're halfway already. I don't know why I can't get it out. We're halfway already. Party's almost over. What a bummer. Okay. So explain how the graph of Y equals negative absolute value of X minus 2 plus 3 can be obtained from the parent function Y equals absolute value of X. All right. Can anybody describe to me the three transformations at play here, and can you describe them in the proper order? Right, just take a moment. I want to give you some time. Can you identify the three transformations, and can you describe how they affect the graph in the proper order? Like, which one would you do first? How does it affect the graph? Which one would you do second? How would it affect the graph? And which one would you do third? How would that affect the graph? Because again, the order in which we do these is important. If we do it in the wrong order, it will kind of throw off our final answer. Okay. So our first manipulation, again, the recommendation is to start with the inside and work our way out. The innermost nested transformation is the -2. We're subtracting a positive on the inside. So it should cause a horizontal change and be the reverse of our intuition. So if we're subtracting 2, that means it should move 2 steps to the positive x, or 2 steps to the right. Okay, so we're starting with the v at the origin. We're going to track the vertex. We're going 2 units to the right. We multiply the outside by a negative. So that's like our y values go from positive y to negative y. So that's going to cause a vertical flip over the x-axis. And then lastly, we're adding 3 outside our base function. So that's going to move the entire graph up by 3 units, okay? So again, starting with a v, going right 2, flip vertically, and then go up 3, and that should be our final graph. Okay, so again, the main takeaway here, when we're doing multiple transformations in one go, the recommended route is work your way from the inside to the out. It's a little bit more nuanced than that, but that'll cover at least 80%, if not 90% or higher, of like the types of questions that we'll have. Yeah, we're gonna let that be for now. Okay, so yeah, I don't know. It always hits me at this hour. Like I'll be fine. And I did not get a chance to take a nap before class today. I usually do, but trying to get grades in order. And it's still, the grades still aren't all the way there, but I had one person message me. I'll go, we'll look at it and see if we can fix it. You know, it's technology just being technology. Okay, so we're starting with absolute value, right, at the origin. The first one we focused on was the -2 on the inside, so that moved the graph to the right 2 units. Then we multiplied the outside by a negative, so it flipped it from the top to the bottom. It flipped it vertically over the x-axis. And then finally, we had a +3 on the outside. So it takes that inverted image and moves it up 3 units. And the red one on the right is our final graph. Final graph. Right? The montage, like final count. Anywho, I'm just sleepy and I'd like to take a nap. What was I watching? Oh, the conspiracy TikToks. Okay, so let's keep going. Okay, so I think that covers 6 of the 10 transformations, all right? The first 4 transformations, actually, I want to say all 6 of those, we call those rigid transformations because they don't distort the shape. They kind of, the shape of it is fixed, but we're just moving the graph around, left, right, up, down, or flipping it top to bottom or side to side. Okay. So then with this example, given the base function absolute value of x, now we want to explore what happens when we multiply the outside by a number larger than 1, and when we multiply the outside by a number between 0 and 1, right? So outside manipulations should cause a vertical change where affecting the y value. The x value should all stay the same. So notice in the chart that we've chosen, our x values all stay the same, and then we have the y values that are going to change. So f of x is the absolute value of x. So then, the absolute value of each of those numbers is not not terribly difficult to do. There we go. Finally got it out. But then g of x. So we're going to take those results from f and multiply each of those results by 2. So we're going to double the results, right? So absolute value of -2 is 2. So then that doubled is going to be 4, right? So on and so on and so on. And then the third part, multiplying the outside by a number between 0 and 1, all right? So let's see how these affected the graph. Okay, so I think most people should be able to populate these numbers or whatever. It's not too terribly bad. So then here, the blue, the absolute value of x is what we were given. Now, I think before we said outside manipulations generally cause a vertical change and they follow our intuition. So here in red, we call this, notice we multiplied the outside by a number larger than 1. We call this a vertical stretch. So it essentially got taller, right? And it kind of followed our intuition. We multiplied the outside by a number larger than 1. It got larger vertically. And then with the green, we multiplied the outside by a number between 0 and 1. So that number is smaller than 1. Our graph got smaller vertically, right? It got smushed. We call that smushing it vertically, do a vertical smush or a vertical compression. Okay. So but that does kind of follow our intuition. Okay. I feel like this is okay. I'm gonna let this be. That's just explaining our result that we got. Okay. So the graph of y equals a times f of x is obtained from the graph of the base function by multiplying the y coordinate of each point on the base function by a and leaving the x coordinate unchanged, right? So again, our x values stay the same. The y values is in the last example doubled or cut in half. So then the result is going to be a vertical stretch away from the x-axis if a is larger than 1, and a vertical compression towards the x-axis if a is between 0 and 1, right? A larger number, it gets larger, it gets further away. Each y value gets further away from the x-axis. If a is between 0 and 1, each y gets closer. It's a vertical compression where each y gets closer to the x-axis. If a is negative, first graph y equals the absolute value of a times f of x by stretching or compressing the graph vertically, then reflect the resulting graph over the x-axis, right? So if we're multiplying the outside by a negative number, right? Sorry. Okay. And so we've looked at multiplying the outside by a number larger than 1. We've also looked at multiplying the outside by a number between 0 and 1. So then what do you think happens if we multiply the inside by a number between 0 and 1? Are you anticipating a horizontal compression or horizontal stretch, right? I already kind of gave you a piece of it. So again, inside manipulations cause a horizontal change, and they're typically the reverse of our intuition. So what that means is if we multiply the inside by a number between 0 and 1, a number that's essentially smaller than 1, then the reversing is going to happen. This is going to stretch horizontally, right? Multiplying the inside by a number larger than 1 is going to cause the graph to compress horizontally. One other thing I want you to keep in mind with this stretching and compressing, stretching a function vertically arguably is similar to compressing a graph horizontally. A vertical stretch essentially is the same thing as a horizontal compression. And you can show that algebraically, right? And then that might pop up. And then similarly, a vertical compression is similar to a horizontal stretch, right? If you squish something vertically, is similar or the same thing as stretching it horizontally, right? Okay. So then we have an example. In part A, we multiplied the inside by a number between 0 and 1. B was larger than 1. And then C is, we'll talk about it. We got time, all right? So with part A, we're expecting a horizontal stretch, because that's a number that's smaller than 1 or between 0 and 1. So it should have the reverse effect. It should cause a horizontal stretch by a factor of 2. Part B should cause a horizontal compression by a factor of 2. And then with C, we would explore the absolute value of 2 times x. And then whatever result we get, we're going to multiply the inside by a negative. Let me see. Yeah, it should flip horizontally. All right. So let's see. I think we have this one worked out. The first one it should be a horizontal stretch by a factor of 2. So it gets bigger horizontally. The next one gets smaller horizontally. So notice this has been smushed by a factor of 2. Okay. And then the last one about the y-axis, right? Horizontal flip. Yeah, that's right. Okay. Okay. All right. So this one, part C, we can do the same as B, but then we need to do a horizontal flip to account for that negative on the inside that we multiply by. Let me check my private chat. I think you guys are okay. Okay, I think you're okay. Okay, we have like about 5 minutes remaining. Okay. Sketch the graph of this function, right? So I could just say it, whoever does the most talking does the most learning. So if I'm the only one talking and seeing it, only reason I know it is because I talk about it all the time. That's why I keep trying to encourage some of you guys to chime in, but it's okay. So with this guy, let me see, 1, 2, 3, 4. This one actually has a total of 4 transformations. Just in the interest of time, I'm just gonna list them out, and then I'll leave it up to you to kind of go back and process that. All right. So the parent function here is what? X squared. And then if we start with the innermost nested transformation, that's going to be that -1. So subtracting a positive on the inside should move the parabola to the right 1 unit. So if we start with the parabola at the origin, we move it to the right 1 unit. Next, we multiply the outside by a number larger than 1. We multiply by the outside by 2. So it's like the x values stay the same, the y values are doubled. So that should cause a vertical stretch by a factor of 2. Then we also multiply the outside by a negative. So that's going to affect our y values, which means that the graph should flip vertically over the x-axis. And then finally, we added 3 on the outside of our base function. So that's going to move the entire graph up 3 units, right? So let's recap this. This is basically a story, right? We're starting with the parabola. Yo. So for whatever reason, I just thought of like, well, can we like make stories out of the formula? And one of my students actually shared one with me. How a formula is a story. I'll go ahead and this is just a tangent, something random. I just want to share. Let me see. So this is how one of my students remembers the quadratic, right? And I'm saying this because this given equation is really a story. It's telling us a story. We're going to come back to that story in just a moment. I want to kind of share this other story with you, right? So this is how one of my students remembers the quadratic formula. The negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m. Like a mini movie, right? Just to remember it. It's a fun way. That's called the memory palace technique, right? So just just a fun way to remember it. Again, the negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m. All right. So then let's see how that correlates to, and that's the quadratic formula, like when you're solving a quadratic function. So then what's the story here? All right. This is basically saying, start with a U-shaped graph, move it right by 1, stretch it vertically by a factor of 2, flip it vertically, and then move it up by a factor of 3. Again, the order is important. If we do it out of order, a lot of times we end up in the wrong spot. All right. A U-shaped graph. We moved it to the right by 1. Okay. Then we said stretch it vertically by a factor of 2, flip it vertically because of the negative, and then went up by 3. We're adding 3 on the outside. Okay. So that's how we're using transformations. Got a couple more. Let's go ahead and wrap this up. Okay, I'll just leave this as an exercise for you. You can use my recording. Let me go ahead and make a copy of this available. Are there any burning questions while I am? If there are, you can like put it in the Q&A or the chat or whatever. Let me see. Let me share. I just wanted to give you a moment to think about what if you have any questions. Here, fall, traditional. Come on. Notes, updated daily. Come on. Okay. Okay. Sorry. So when this window closes out, you'll receive a copy of any. I didn't really write anything, but you'll receive a copy of our notes from today. So what we did today, we kind of explored the total of 10 transformations. The first six were we call those rigid transformations because they don't distort the shape, they just change the position or flip it vertically or horizontally. The last four with the stretching and compressing, those are non-rigid transformations because they distort the shape of our graph. Um, you know, just do your best to try to get started as early as possible. Practice, team up, that spiel. If there aren't any burning questions, we're going to go ahead and end the session here. On Wednesday, we'll go through as many of the corresponding homework questions as together as we can. And if there aren't any burning questions, we'll end the session here. And from one beautiful mind to another, enjoy your afternoon. We'll meet back on Wednesday, same time, same place. I'm removing my microphone now if anybody needs to speak audibly. All right, guys, take care. Peace. Let me see. So, as usual, I do have another class that starts in 15 minutes. I'm going to let it keep streaming. I'm just going to suppress my audio, and I'll be just chilling here for the next 15 minutes to my next class.
Hello?
Yes.
So I just joined off my phone. I tried to join on my computer, but the internet in my building isn't working. I emailed you a little earlier.
You are you in the 2 o'clock class?
Yes, sir.
Yeah, don't worry about it. I'll update the attendance later. If you don't get credit, just remind me, and we'll make sure that you get credit.
Okay, thank you so much. And I was watching the YouTube, so
Okay, okay,
okay.
okay.
All right, thank you so much.
Uh-huh.
Have a great day.
All right. See what we're looking like. What you looking like? What you looking like? Hey. All right. All right, gentlemen. So welcome. Let's see. So the main thing, I did update grades. I will say they more than likely are not 100% accurate, which is okay. The main thing that we need to confirm is that the scores that you're getting in Blackboard have ported into, sorry, the scores that you're getting in my math lab have ported into Blackboard, right? I had one student contact, he was concerned because he was like, my grade was I guess like an 88 and it dropped to an 82. And so I didn't get a chance to tell him because he messaged me while I was in class, but I changed the weights, right? I think whatever the weights it had, everything was evenly distributed. I reset it so that it's closer to how it's going to be like as your final grade, right? So, like for instance, your overall grade in my math lab right now, and you guys have the lab as well. That's something separate. We'll try to talk about that too. But in my math lab, I think I scaled your homework so that it counts as 10% of your overall grade. Your quizzes count for 10% of that overall grade, and then the exams count for 80%, right? So, they'll explain your score in like my math lab. And then as far as like the midterm, so I think the grading rationale that I did, I said that the homework was like 9%, quizzes were 9%, exams were, I think it was 54%, and then the lab was 10%. So, you know, so that's how I calculated like the rubric for the midterm grade. And then so again, that's not these grades right now. This is just a snapshot of where you are at this moment in time. Oh, also by the way, I'm using my microphone, so I'm not going to be able to hear anybody until the end after everything. But yeah, these like the midterm grades and any grades updates we do along the way, they're just a snapshot of where you are at that moment in time. It has no bearing on the grade that matters, which is the final grade. So on your end, as long as you're getting your assignments in with satisfactory scores in time for the final, and I'll try to like check in periodically to make sure that the grades that you're earning in my math lab are showing up in Blackboard, because I definitely had a couple of instances where the grades wouldn't port for whatever reason. I don't know why. I wasted a lot of hours trying to figure out, okay, I can see the grades in my math lab, but they wouldn't show up in Blackboard. So some of the grades I did have to enter manually. This is why it's important to check your grades for accuracy. It won't be 100% accurate until the end because we have to take the final exam before we can get a true reading. So this is just a gauge, and just make sure that your grades are porting properly. So if you see a shift or a drop in the grade, also, so if your grade is lower than you were like, keep in mind that we get unlimited attempts on our assignments. So you can actually go back and boost your score. If you are like going back and submitting assignments to boost your overall score, my recommendation is to prioritize the exams. Again, the exams have a heavier weight than the homework and quizzes. The homework is going to be a lot of work for minimal points. It's really there for you to practice to get ready for the exams. And then once the exams become available, that's your opportunity to like really be compensated for you showing what you know. So again, if you are going back, try to get your exams in order first, and then maybe prioritize the homework last, because that's going to be a lot of work for minimal points. Okay. If you have questions, for right now, you're going to have to either use the chat or the Q&A. And we're sorry. Ooh, I kind of had like a sneeze, but it didn't want to sneeze. So I was like, come on, no. It just went back. I was like, no, I'll come back later. So what we're going to be working on today is basically the next installment, right? So last time we worked on section 1.4, a library of functions. Some of the base functions or parent functions that we explored were the constant function, which is a flat horizontal line, identity function, which is the diagonal line, squaring function, which is basically a parabola, cubing function, which is like an S shape almost. Then we have like the square root function, which is the top half of a sideways parabola, absolute value function, which is a V, greatest integer function, which is like that step function, and the reciprocal function, which is like the 1/x deal, right? So we're going to take those library of functions and start applying transformations to these or manipulating these guys. So it's this one. Okay. So today we're going to be working on section 1.5, transformations of functions. One, we like to define transformations of graphs. Two, use vertical or horizontal shifts to graph functions. Three, use reflections to graph functions. And four, use stretching or compressing to graph functions. I want to say almost in every class I have like one student that has temporary access, or and those basically lock out after 2 weeks. And so any work that you do, if you're, it'll be saved, but to get credit, you got to be sure to get access as soon as possible. I felt like there was something else I wanted to say, but I can't think of it. Yeah. So transformations. If a new function is formed by performing a certain operation on a given function, f, then the graph of the new function is called a transformation of the original function, right? The transformation of the graph of f. Okay. So given this base function absolute value of x, we want to consider g of x, which is absolute value of x plus 2, and h of x, which is absolute value of x minus 3. We're asked to sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graphs of f. So if we were going to plot these on the same coordinate plane, we can choose several values of x, find the corresponding f of x, and then also use those same values of x to find g and h. Okay. So then absolute value, right? Absolute value is the positive distance the number is away from 0, right? So then we're basically making a table. So the x values that we chose were -5, -3, -1, 0, 1, 3, 5. So the absolute value of -5 is 5. Absolute value of -3 is 3, so on and so on, right? It basically forces the number to be positive. Yeah. So then for this g, which is absolute value of x plus 2, essentially what we're going to do is take the results from y and add 2 to all of those results. So then when we plot the ordered pairs that's generated by this scheme, then we get this image on the right, where the blue is our original function absolute value of x. Okay. Notice that adding a positive on the outside of our base function move the new graph up, in this case, 2 units, right? Let me say that one more time. Adding a positive on the outside of our base function move the original function up that many units, right? So notice that the outside manipulation caused a vertical change and it followed our intuition. Let's say that one more time. And the outside manipulation caused a vertical change and it followed our intuition. So if adding a positive on the outside caused the original graph to move up that many units, then what does your intuition tell you that subtracting a positive on the outside, how is that going to affect the original graph? Anybody got a result in the chat? Let's say it one more time. So if adding a positive on the outside caused the original graph to move up that many number of units, then you can anticipate subtracting a positive on the outside to do what? Go once, one twice. All right, let's see. Let's see what happens. So we're still using the same values of x, and we're going to compare our h of x to our base function f of x, all right? So the first 2 columns are the same, but now in that third column, instead of adding 2 to each y, we're going to subtract 3 from each y, okay? We generate these numbers on the right, and so we could, when we plot the points, we get the image we get the image on the right, right? So, so the blue is absolute value. That's where we started. And we see that subtracting a positive on the outside confirms our intuition where we move the original graph down 3 units in this case, right? So adding a positive on the outside of our base function, move the original graph up that many units. Subtracting a positive on the outside of our base function, move the original graph down that many units, okay? So given a positive number c, the graph of f of x plus c, notice that plus c is outside our base function. This is going to be the graph of f of x shifted c units up. And then the graph of f of x minus c is going to be the graph of the original function shifted c units down, right? So that's just kind of reiterating what we said a moment ago. Okay. So then in this example, we're starting with a squaring function, y equals x squared. And then, so for g of x, we're going to see how does it affect the graph when we subtract 2 on the inside or when we add 3 on the inside, all right? So subtracting a positive on the inside, something happens. Adding a positive on the inside, something happens. Okay, and so we'll do this in similar like we did the previous. We'll choose several values of x, find the corresponding f, find the corresponding g, and find the corresponding h. Okay. Now in that previous example, notice that the x value stayed the same, but the y values changed in the previous example. In this example, you can kind of argue this as the x values are changing and the y values are staying the same, right? So like on the left-hand column, we chose several values of x. We found the corresponding y. And then when we incorporate the transformation of subtracting 2 on the inside, notice the y values are still there, but they're now just associated with a different x value. So essentially the x values have changed and the y values have stayed the same, right? Okay. So what does your intuition tell you happens with this graph, right? Before, adding a positive on the outside caused a vertical change and and it went as such. So then if you had to guess, subtracting a positive on the inside, what do you think happens? What do you think happens adding a positive on the inside? If you think that this is going to move the graph left 2 units, you are absolutely incorrect, right? The whole point is that inside manipulations, they do cause a horizontal change, but they're generally the reverse of our intuition. Even though we subtracted a positive on the inside, it caused our graph to move in the positive x direction, right? So one way to kind of keep track of that, whenever you're doing inside manipulations, like in this instance, you got to ask yourself, what value of x is going to make the inside 0? Well, positive 2 is going to make the inside 0. So that means we move the original graph 2 units to the right. If we look at the red, what value of x makes the inside 0? Oh, well, -3 would make the inside 0. So then we move the original graph left 3 units. 3 units, right? Outside manipulations generally cause a vertical change, and they typically follow our intuition. Inside manipulations tend to cause a horizontal change, and they're generally the reverse of our intuition. Okay. Okay. And then, so when you start applying the transformations yourself, you get a final answer, maybe choose a few test points to make sure that it all lines up. Choose several values of x, find the corresponding y, and it should match whatever graph you've created at that point. If it doesn't, either you did your calculations wrong or you did the transformations wrong, right? Yeah, I'm kind of suffering. Like, I normally do not do dairy at all, and I got some. They didn't have the potato salad I normally got. I normally like to get. They had New York style, and I was reading the ingredients, and it said like mayonnaise. I was like, oh no. and so now I have all this mucus because I introduced some dairy into my system where I normally don't eat dairy. So now I have to like flush it until I can get it out of my system. Okay, so we've explored, these inside manipulations and how they affect the graph. Okay. So then given a positive number, subtracting a positive on the inside of our base function is going to shift the original function C units to the right. And then adding a positive on the inside of our base function shifts the original function C units to the left. So again, each of these like transformations in and of themselves, they're not difficult to process. But the challenge comes, this stuff kind of is like information overload. At this point, we've covered a total of 4 out of the 10 transformations. The only way I know to kind of mitigate the information overload is to start as early as possible. The more time you give yourself to let this stuff marinate, the less likely you're gonna experience that anxiety or whatever. I lost track of what I was saying in the middle of the sentence. I was trying to pull it back, but I'm also like really sleepy. I struggle with my 2 o'clock. And the only reason I didn't get a chance to take a nap today before class, like I know, you got to take a nap. Napping in the middle of the day like a newborn pup. That's a movie reference, by the way. I don't know if you guys know that or not. Only reason I didn't get a chance to take a nap because I was trying to get those midterm grades in order. In the past, normally what I would do is like export the grades from my math lab. I put it into like numbers. I create my own formulas, and it's real smooth. I like it. So this semester, I've noticed that all of these platforms, they made it easier for the grades to like there be a live update with the grades between Pearson and Blackboard or Pearson and a digital campus. So I was like, okay, well, since they're making an effort to update this, let me make an effort to actually use the system. And so it took me a little while to kind of like figure out some things. And it's still, all the bugs aren't 100% worked out, but it does seem like it'll be live updates on your grades. Like once things are set up and you start submitting more assignments, if you go back and change something, it should update your grade automatically. If it doesn't, as long as you're showing in Pearson, it will get ported. You know, at the end of the semester, you're definitely going to want to check to make sure that all of your grades have ported properly. Okay. So let's look at this example. We're asked to sketch the graph of the function. Okay. All right. I think we talked about the shape of this earlier at the start of class. So the parent function here is square root of x. All right. The general shape of square root function is the top half of a sideways parabola. Okay. So we can use transformations to graph this. If we start with the top half of a sideways parabola, we have 2 transformations at play here. So one thing I want to mention is that whenever we're doing multiple transformations in one function in one go, the recommended order is to start with the innermost nested transformation and then work your way out. So for instance, in this example, our innermost nested manipulation is going to be that +2 because it's inside the radical, right? It's the innermost nested. So adding a 2 on the inside should shift the original graph left 2 units. Okay. It should shift the original graph left 2 units. And then subtracting a positive on the outside should shift it down 3 units, right? So this is a story. Basically, the story is saying start with the top half of a sideways parabola, move the image left 2 units and then down 3 units, and that's going to be the final graph. Okay. So the parent function is square root of x. They rewrote it so that it's x minus a number. I mean, that's fine. All right, x minus a number plus a number. So then, again, inside manipulations cause a horizontal change is the reverse of our intuition. Intuitively, we might be tempted to move it in the positive x direction, but that's actually going to move in the negative x direction. And then we go down by 3. So they're essentially repeating or reiterating what we did a moment ago, what we've kind of talked about. Okay. And here's a pictorial representation. So the black curve is the original curve, where that's going to be just a square root of x. And then we move what? The x plus 2 is going to cause the original graph to move left 2 units. And then that -3 being on the outside causes the original graph to move down 3 units, right? Okay. So we've explored 4 of the 10 transformations. These 4 thus far are what we call rigid transformations, because they don't. We call them rigid transformations because they don't distort the shape of the graph. They only just move the graph side to side or up and down, right? So now we want to explore what happens if we multiply the outside by a negative, right? Outside manipulations generally cause a vertical change and they follow our intuition. So if we multiply the outside by a negative, our x values are going to stay the same. Our y values are going to go from positive to negative. So when that happens, that's going to cause our original graph to flip vertically over the x-axis. I feel like I'm doing like the world's most like boring story time because like I feel like it's like I'm chatting. It's a little bit difficult because we're not really doing a back and forth. It's just a little bit of a challenge to do back and forth. So I'm kind of treating it like I'm telling a story, but I'm like super sleepy and the topic is kind of like boring, and I was like, I mean, we could like do some other things, but we'll work on some other stuff a little bit later, right? So here, so this is an example of like multiplying the outside by a negative. Notice that our x values stayed the same, but our y values went from positive y to negative y. So it caused our original graph to flip vertically over the x-axis. Okay. Okay. So that's multiplying the outside by a negative. So then let's look at multiplying the inside by a negative. Reminder, inside manipulations generally cause a horizontal change and are generally the reverse of our intuition. So the graph of f of negative x is a reflection of the graph of f of x across the y-axis. If a point x comma y is on the graph of f of x, then the point negative x comma y is on the graph of f of negative x, right? So again, multiplying the inside by a negative, it makes our x values go from positive x to negative x. The y values should stay the same, right? Okay, so it causes a flip horizontally over the y-axis. So for instance, if the blue curve, f of x were our original function, and we multiply the inside by a negative, then again, the y values stay the same, but the x values went from positive to negative. Okay, so multiplying the inside causes a horizontal flip over the y-axis. Okay, so in this example, we're asked to explain how the graph given can be obtained from the graph of y equals absolute value of x. Okay, I think I'm just going to walk you through this one. So the parent function here is the absolute value of x, right? So that graph is just a v where the vertex is at the origin. I think a slide or two ago, we mentioned something that whenever we're doing multiple transformations in one go, the recommendation is to work your way from the inside to the out. So the innermost nested manipulation is going to be that -2, right? Subtracting 2 on the inside to move the original graph right 2 units. The next one would be multiplying the outside by a negative. So outside manipulations are going to affect our y values. So it's like our y values are going from positive y to negative y. So that's going to cause our graph or our image to flip vertically over the x-axis, right? And then lastly is the +3 on the outside. We're adding 3 on the outside. So that's like adding 3 to every y value. So the x values stay the same, but our y values go up by a factor of 3, right? So the story that this equation is telling us is saying, start with the v where the vertex is at the origin. And if you track the vertex, we're going to move the graph right 2 units, flip it vertically over the x-axis, and then move it up by 3. Okay. So then we're starting with our v with the vertex at the origin. We went to the right by 2. We flipped vertically over the x-axis, and then we went up by 3. And that's how we got that image. Now, this doesn't always work, but you could verify that, if you don't do it if you don't do the order working from the inside to the out, you can verify that you get a different result. Like you could try changing the order or doing it in a different order and see if you get a different answer. sometimes it happens that way. Like if the order will affect, it doesn't always affect the final image, but there's enough times where it does affect it. So again, the recommendation when there are multiple transformations, work your way from the inside to the out. Okay. All right. So we've seen our 6 rigid transformations. The first 4 maintain the shape but move the graph either side to side or up and down. And then manipulations 5 and 6 were multiplying the outside and the inside by a negative, right? We multiply the outside by a negative. It flips vertically over the x-axis. Our y values go from positive y to negative y. If we multiply the inside by a negative, our x values go from positive x to negative x. Our y values stay the same. So now we want to extend it a little bit further. And we want to see what happens when we multiply the outside by a number larger than 1 versus multiplying the outside of our base function by a number between 0 and 1. Okay, so we're asked to sketch the graphs of f, g, and h on the same coordinate plane and describe how the graphs of g and h are related to the graph of f. So if our parent function here is absolute value, we know how to find the absolute value, right? So you can easily fill in that chart. And then for like g, you would let x be -2. Absolute value of -2 would be 2 times 2 would be 4, right? Okay, and so, I feel like filling in the chart here isn't too terribly bad. Okay, so if we put all this information together, we get an image like this, right? Where the blue is our base function as absolute value of x. Multiplying the outside by a number larger than 1 cause the graph to get larger vertically. So we call that a vertical stretch, right? Multiplying the outside by a number between 0 and 1 yeah. So notice that the number on the outside is smaller than 1, so it caused our graph to get smaller vertically. We call that a vertical compression or a vertical shrink, okay? So here are 2 more, these are 2 more transformations. These are called non-rigid transformations because they're going to distort the shape of our graph, right? Okay. So if we were to multiply the outside of our base function by some a, we're going to experience a vertical stretch away from the x-axis if a is larger than 1, and we're going to experience a vertical compression towards the x-axis if a is between 0 and 1. If a is negative, first graph the absolute value of a times f of x by stretching or compressing vertically, then reflect the resulting graph about the x-axis. So we flip it from the top to the bottom whenever we multiply, if a were less than 0, right? Sorry, let's see. Okay, so we explored multiplying the outside by different numbers. So then we also want to consider multiplying the inside, right? Inside manipulations generally cause a horizontal change and are typically the reverse of our intuition. So say we multiply the inside by a number between 0 and 1. Intuitively, well, we're multiplying it by a smaller number, we might try to make it smaller horizontally, where in reality, that's going to cause a horizontal stretch, right? Multiplying the inside by a number between 0 and 1 is going to cause a horizontal stretch by that factor. And then multiplying the inside by a number larger than 1 is going to cause a horizontal shrink by that factor. Okay. So in this example, we're asked to use the graph of a function y equals f of x in a figure whose equation is not given. And we're asked to sketch each of the following graphs. In part A, we multiplied the inside by a number between 0 and 1. Part B, we multiplied the inside by a number larger than 1. And then part C, we multiplied the inside by a negative number, okay? So multiplying the inside by a number between 0 and 1, it should be a horizontal change, and it should be the reverse of our intuition. So that means it's going to cause a horizontal stretch, right? Multiplying the inside by a number between 0 and 1 should cause a horizontal stretch by a factor of 2 in this case. Multiplying the inside by a number larger than 1 we know it's going to cause a horizontal change. Intuitively, we might think it gets bigger horizontally, but in reality, it shrinks horizontally by a factor of 2 in this case. Okay. And then C, the recommendation is analyze like absolute value of 2 times x, right? So if we just said the absolute value of 2 times x, that would be like B. So then let me see. That will cause a horizontal shrink by a factor of 2. Then we multiply by a negative. That's going to cause our y values to go from positive y to negative y. So it should flip vertically over the x-axis, right? For that third one. Okay. Okay, let's see what do we have. So notice the first one did stretch horizontally by a factor of 2. The second one was compressed horizontally by a factor of a half, I guess you could say. And then finally, if we multiply by -2 on the inside, it should flip horizontally. I think I said vertically before. It should flip horizontally, right? So again, let me see. Let's try to wrap this part up. Let me see the time. Oh, we got a good amount of time. Okay, let's go ahead and do this one. All right. So here, we have several transformations in one go. Can anybody identify the parent function and describe what it looks like? Can anybody do that in the chat? What's the parent function here? And what's the general shape going to be? All right. And then a follow-up question to that would be, we have a total of 1, 2, 3, 4 different transformations. Can you not only identify the base function, can you identify what are the 4 transformations, how do they affect the graph, and what's the proper order in which we should apply these transformations? All right. Just take a moment. Even if you're not like, if you're nervous about answering, just take a moment to think about that. All right. Let me say it one more time. So the challenge here, can you identify the parent function, the base function? And then the claim is that there are a total of 4 different transformations at play. Can you identify the 4? Can you express them in the proper order? Identify the 4, express them in order. There was another part, but I'm drawing a blank. Yeah, express them in the proper order and then describe how they affect the graph, right? So let's go ahead and take a look at this, right? So the parent function here, hopefully you're thinking is a squaring function, y equals x squared, right? So a parabola, right? U-shaped curve. And so when we apply these transformations, the recommendation is to kind of track the vertex, all right? Track the vertex, and it kind of makes it a little bit easier to keep up with where it is and what's going on. So we start with the parabola where the vertex is at the origin. And we're going to work our way from the innermost nested manipulation, work our way from the inside to the out. So the innermost nested transformation is going to be that -1. Subtracting a positive on the inside should move the original graph to the right by 1 unit, right? Okay, again, inside manipulations are generally the reverse of our intuition. So then the next transformation is, now we're working our way to the outside because we've done all we can do on the inside, is the 2. Right now, we're going to ignore the negative for right now. If we multiply the outside of our base function by a number larger than 1, that's going to cause a vertical change in follower intuition. So that should cause a vertical stretch by a factor of 2. Okay. Then the next one is we're multiplying the outside by a -2. Sorry, by a negative. So multiplying the outside by a negative is going to cause a change in the y value. It's like our y values are going to go from positive y to negative y. So we're going to, that negative is going to have us flip the graph vertically over the x-axis. And then finally, we're adding 3 on the outside of our base function. So that should cause the original function to go up by a factor of 3. Let's recap this before we look at the result. So we're starting with a parabola, a U-shaped curve. If we track the vertex, this is saying go right 1, stretch vertically by a factor of 2, flip vertically over the x-axis, and then move up by 3. And that should be your final image, right? So again, it's like instructions or a story. So we started with the parabola with the vertex at the origin. We went right 1 unit, did a vertical stretch by a factor of 2, and then flipped it vertically over the x-axis, right? So this is the image that we were describing. Okay. Oh, and then shift the graph 3 units up. Okay. Let me see. So, okay, so for an artery with a radius of r, capital R, the velocity v of the blood flow at a distance r from the center of the artery is given by this formula. Let me see. An artery with a radius of r, the velocity of the bloodstream flow at a distance r from the center. So r from the little r is like the radius. Wait a minute. The velocity of the blood flow. Okay. So the little r is telling us the distance the blood flow is from the center. Okay, that's fine. Where C is a constant that is determined for a particular artery, write V of R equals to, we write the velocity based on R as this guy, so that's given. Starting with the graph of Y equals R squared, sketch the graph of V of R given that the artery has a radius of 3 and C is 10 to the power of 4. So big R they give us, we're letting little r kind of like it's an X, and C is 10 to the power of 4. Okay. Okay. So if we start with R squared, right? That graph would just be a parabola by itself. Okay. So I want to say that the next transformation would be multiplying the inside by a negative, which is going to cause the original graph to flip horizontally over the y, right? So I don't think it is really going to show an effect because the parabola is already going through the origin. So if we flip it horizontally, we're going to get the same image. Then we're adding that R2, which is it's just gonna be a constant at this point because we're gonna let R be 3, right? Which is 9. So it's like we're adding 9 on the outside of our base function. That should cause the original graph to move up 9 units. Okay. And then multiplying the outside by a number larger than 1, that's going to cause a vertical stretch by a factor of, it looks like 100,000? No, 10,000, right? 10,000. Yeah. Okay. Okay. So we started with the parabola. Did they distribute? We said we started with the parabola. Oh, wait a minute. I don't think we said anything about it going upside down. Because if we flip it horizontally, we go, that moves it to the right. They distribute it. Why did they reflect? How did they get it upside down? Are we missing something? No, it's not there. That's a positive number. They flipped it horizontally. Mm-hmm. Hmm. You could rewrite that. Why are they reflecting? Is this image right? Yeah, it should be. It should be going down. Okay, so sometimes it helps to rewrite this. Like right now, we have what, that 9 minus r squared. We could factor out the negative, move the negative to the outside, and rewrite it as r squared minus 9. I'm trying to think why. Is that considered something on the outside? Oh, okay. I see. I think I see it now. Okay. So what they ended up doing we should have written it out, but what they ended up doing was they distributed the C, right? So if you distribute the C, you're going to have 9 times the 10,000 minus. They basically, yeah, you know what? I see what I did. Because of the parentheses, I was thinking that was inside manipulations, right? That was not inside the base function. If it were inside the base function, the squared will be on the outside of the parentheses. So all of those manipulations are actually outside manipulations. That's why I was like, why am I getting this wrong? I was getting it wrong because I was thinking those were inside manipulations, and they're not, right? They're vertical. They're vertical manipulations because they're outside the base function, right? So if you distribute it, it makes it easier to see that those are outside manipulations. This is saying start with the, so right here. This is saying start with a U-shaped curve, stretch it vertically by a factor of 10,000, flip it vertically, and then move it up by a factor of 90,000. All right. So I think the parentheses threw me off, and I was treating these like these were inside manipulations, and it was giving us the wrong image. If we had generated an image that was wrong and we did a few test points, we'll see like, oh, wait a minute, this isn't right. We're not seeing something right. I had to go back and think about it. Again, these are outside manipulations because the parent function is here. They're outside the parent function. Inside the parent function, it will look something like this. All right, it would look something like that. So that means all of these guys are outside manipulations. That's how we got it upside down. Okay, not too bad. Part of it is up sleepy, but we're at the end, so you know. So the portion of the graph corresponding to negative values of R do not have any physical significance. That's fine. Okay. So yeah, the main thing there was just realizing that those were outside manipulations and not inside manipulations, right? Okay. All right. So I feel like there should be questions. Let me go ahead and make a copy of this available and do some closing remarks, and we'll get out of here. So when I say get out of here, you know, that made me think of with the box season 7, one of the contestants, I swear, they were like a live action animation. Cause like, you know, those like classic New York style cops. Hey, yo, what are you doing? You see me walking here? Get out of here. Oh, you like apples? How about apples? Like that, those guys talk like that literally the entire time. I was like, are they putting on a show? Like, there's no way that these guys really talk like this the entire time. I mean, and they did. And it was really funny. Like, it really just, I felt like I was watching some kind of comical movie. It was hilarious. It'd be like, and then so like they were catfishing as one of their girlfriends, one of their girlfriends. And so they'll be responding, hey, yo, Shirley, I think that, you know, it was hilarious. You know, and so again, the conclusion of it all happened. It concludes in like a couple of days. So this weekend, while I was out, I was thinking to myself, I was like, "Yo, I know that season 6 and 7 were filmed here in the city of Atlanta." So I was like, "Let me see if I can go find the building." I was like, "Oh, sure enough, I found it." I was like, "Oh, that was fun." You know, I didn't bother trying to go in. My companion at the time was a party pooper. She was like nervous. I was like, "Why are you nervous? It's not a big deal. You just go in and talk to people, then you just leave. Like, ain't nothing gonna happen." So, you know, but we did find it. That was fun to drive past there. At least for me. For whatever reason, she was nervous. I'm like, I don't understand why you're nervous. What if we wanted to like look at a room and we were just scouting and we just wanted to get some information? Like it's the same thing. They don't know, you know. So anyway, so let's do some closing remarks and kind of let you guys go. So again, I did update grades. You definitely on your end, you want to check your grades in Blackboard for accuracy. Any grades that you see now, they're just a snapshot of where you are at this moment in time. They don't really matter. It's just to give you some feedback so that you can get a sense of what I see on my end. If anything looks like it's missing or is out of order, you have to bring it to my attention so that we can try to resolve it. The only grade that really matters is at the end. Okay, is the final grade. Okay, and so all the way up until the final, you have an opportunity to change any assignment, even exams. If you are going back and completing old assignments to boost your overall score, my recommendation is to prioritize the exam first, as that's going to have a much heavier weight than like a homework or quiz. Homework is going to be a lot of work for minimal changes in your overall score. If you want to see moves, you got to maximize the score on your exams. Okay, so hopefully. again, if there are any, I'm gonna remove my mic in just a moment. If there are any burning questions, when I remove my mic, feel free to ask. Otherwise, if there aren't, we're gonna go ahead and end the session here. And from one beautiful mind to another, have a great afternoon, gentlemen. And we'll meet back on Wednesday, same time, same place, to go through as many of the homework questions together as we can. All right, gentlemen, take care. I'm removing my mic now. If you have any questions you need to speak about audibly.
Excuse me, Professor C.
Uh-huh.
So we don't have a midterm?
Okay, that's a good question. So no, the midterm grade basically
Is our grade what's in there now?
Yeah, just whatever was due. So just those first few assignments along with exam one, and that's it. I just did the grade.
All right, so our grade that's in there now, that's also averaged out from the lab grade too?
Yes.
Okay, so that grade in there now is like our grade that's gonna be on midterm.
But it doesn't. It doesn't matter. It's really
Yeah.
just a snapshot. It's just so that you can have a sense of like you don't want it to be where, hey, I know I did this assignment, but I don't see credit for it, right? So you just want to make sure that your assignments are there. These
Yeah,
grades,
all right.
they're going to be changing until we finish the final exam.
Yeah. All right.
Yeah. So there's a good question. Any other questions, gentlemen? We'll go separate ways going once. All right, gentlemen. Otherwise, okay. Have a great afternoon, and we'll meet back on Wednesday, same time, same place to go through the next installment. All right, guys. Take care. Peace.